Hello. Today I'm going to show you how to implement a 4-variable Boolean truth table using a 4-to-1 MUX in standard gates. In a 4-to-1 MUX, there are 4 inputs and 1 select or switch and 1 output. You're probably curious, how do you turn a function with 16 inputs into only 4 and have it output the same exact thing? Well, we use a MUX in this situation. Here are your 4 inputs, here's your select or your switch, and here's your output. When you have a 16 variable truth table, you can go about it a couple different ways. You can make your switch ABC, you can make it BCD, you can make it CD, you can make it AB. In this particular situation, we're going to end up making it CD, and you're going to have 2 variables you're dealing with when you're implementing your 4 inputs. So this right here is the function I've provided to first build the truth table. There's a little twist on this problem where inputs 10 through 15 are what we call don't cares, meaning that we can manipulate them to what we want them to be. In other words, their output has no effect on the intended function of the circuit. First, we need to fill in our kernel map, or K-map for short, to help us get a better grip on what we're dealing with here. Squares of the K-map, they correspond with the inputs of the truth table that you're representing with the K-map. They correspond in this way: 0, 1, 2, 3, 4, 5, 6, 7, 12, 8. You gotta jump down a row: 8, 9, 10, 11, 12, 13, 14, 15. I'm going to quickly fill it in here. I am just assuming that you all have dealt with K-maps before. If not, just go look it up very quick, briefly. It's not hard to understand how to fill one of these in. Might be a little more difficult to understand how to use them, but you don't need to actually know that for what we're doing with it now. Okay, now what we're going to do is we're going to break it down into 4 columns. Like I said earlier, our CD, which is represented across the top, is going to be the switch of our 4-to-1 MUX. So we're going to call this I0. We're going to call this I1. Now to go to I2, you got to jump. You got to remember, you got to jump. This will be I2. This will be I3. Now we will break this problem down even further by making a truth table for each of the 4 columns we just dictated to ourselves. From these 4 truth tables, we will derive what kind of gates we will use to input AB for our 4-to-1 MUX. I hope by this point you're beginning to see the correlation here. If not, no worries, it'll make sense to you by the end of the video, I can promise you that. Okay, so start with I0. I0 is when CD equals 0, 0. So now we're left with AB. Now we have a 2-variable truth table. Now what does Y output when AB goes through all of this? 0, 1, gotta jump, 1 star. Now we're gonna turn this star into a 0, because remember, we can manipulate it. I hope this truth table looks familiar to you. If not, I'm just going to tell you it is A exclusive B, or a XOR gate. This is your I0. Now we're going to do I1 when CD equals 0, 1. Two-variable truth table. 0, 1, 1 star. but you can guess we're going to change this star into a 0, and we again have A exclusive B, or a XOR gate. Now, this is going to be your I2 when CD equals 1, 0. Your two variable truth table. 1, 1, star, star. 1, 1, star, star. Now we're going to change this star into a 1 and this star into a 0. And what we have here is actually a NAND gate, which is A and B all knotted. Now we're going to deal with I3 when CD equals 1, 1. Set up your two variable truth table for AB, and you have 1, 0, star, star. 1, 0, star, star. We're going to change the two stars down here into zeros. And I don't know if you recognize this truth table, but what this is A or B knotted, or just simply a NOR gate. Now we can implement this. We can now build our 4-1 MUX. Our switch is our CD. Our four inputs, I0, I1, I2, and I3, we'll implement them using a XOR gate, a NAND gate, and a NOR. I'll now draw this. I've set up the skeleton again for the sake of time here. But this will represent our A wire, this will represent our B wire, and this will represent our switch. This, I0, I1, I2, and I3. Now, since I0 and I1 are represented by a XOR gate, we can actually just draw one single XOR gate and duplicate the output. Duplicate. Connect your A wire, and you connect your B wire. For I2, we decided that was a NAND gate, which is just an AND gate with a NOT on the end. Connect your A wire, connect your B wire. I3, we decided was a NOR gate, which is an OR gate, and you guessed it, with a NOT on the end. Oh, that's supposed to be connected right there, okay? A, B, okay? And your output. This is your 4-1 MUX from a 4-variable truth table. Now, I'm going to do one last step here. This is not necessary whatsoever, but for those of you who aren't following at this point, I'm going to break it down even further with one last truth table. Now, remember I said our switch, which is S1 and S0, this is S1 and S0. I just didn't write that, I didn't want to confuse anyone, but this is what CD is representing. So your switch, when CD is 0, 0, that lights up input 0, okay? And when input 0 is lit up, it goes through AB, okay? And AB goes through 0, 0, 0, 1, 1, 0, and 1, 1. when CD is lit up. And we said it was a XOR gate. So I0, 0, 1, 1, star, which we decided was a 0. XOR gate. I1 was the same thing. 0, 1, 1, star. XOR gate. I2 was 1, 1, star, star. We went 1, 0, which was your NAND gate. And then I3, when CD is 1, 1, that means that input 3 gets lit up. 1, 0, star, star, which we turn both stars into zeros to implement our NOR gate. Now, very briefly, I'm going to show you the correlation here. Okay? I0, when CD equals 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, star. 0, 1, 1, star. And it works like this through the entire truth table. So this is your final answer. Thank you for watching. If you have any questions or comments or constructive criticisms, do not hesitate to comment. Also leave suggestions for anything else you might not understand. I'll be happy to explain it. Thank you.